6.2 FNC Derivation via construction, a leading order analysis. Now consider neighboring geodesics. The equation for geodesic deviation in the neighborhood of the closed null geodesic, CNG, can be studied in FNC using MTW convention, with vectors E sub alpha and with metric second order in spatial displacement. Thus, in FNC coordinate system all G sub alpha beta comma gamma terms are 0. So have equation 6-31. Consider equation 6-32. Geodesic equation. See the equation. In FNC coordinates, this is see the next equation shown. Thus see the equation.
And also have see the next equation shown. So,
see the group of equations.
Let's now consider correspondence of appropriate orders to get constructive derivation. Fermi coordinates. Equation 6-33. Recall that see the equation. What are gamma sub mu beta gamma and, thus, see the next equation shown. Use, see the equations shown.
Here, our sub alpha beta gamma delta vertical bar sub G is the tensor evaluated at G. Next, consider see the equation. This is taken along the geodesic, so usually has a T, and we have see the next equation shown. Dependence in the FNC system. Here, due to the axial symmetry, the CNG that we are regarding as G must have see the equation. For the spatial case of CNG as G, the FNCS will have no time dependence to all orders since our sub alpha beta gamma delta vertical bar sub G is terms independent.
See the following group of equations.
And for the pure spatial gammas, see the group of equations. Thus equation 6-34. Carrying out the asymptotic match analysis is then done with G's, gammas, and R's. Recall that see the next equation shown. And beginning with the metric.
See the equations shown. Now the gammas.
See the following group of equations. Now the R's. See the equation.
And see the next equation shown. Due to axial symmetry and to O of the absolute value of x, otherwise see the group of equations. So see the equation. The following was useful in the above.
See the equations shown. Using see the next equation shown. And see the equation.
We now have see the following group of equations.
Thus, equation 6-35. And our sub alpha beta 00 equals O of the absolute value of x equals 0 by antisymmetry. 6.3 Full derivation of FNC and geodesic deviation from geodesic equation Levi-Civita. Consider the geodesic equation. Gradient sub kk equals 0 equation 6-36. Consider a 1-parameter family of geodesics E of s comma tau with tangent vectors the alpha power of k of s and associated connections gamma of E comma where tau is the affine parameter and s is a continuous index over the family of geodesics. Equation 6-37.
So, see the next equation shown. Is a geodesic equation. For any of the geodesics. Equation 6-38. Equation 6-39. Equation 6-40. Only have alpha equals I non-zero, see the equation. To lowest order, equation 6-41.
Equation 6-42. Equation 6-43. Recall see the next equation shown. While see the equation.
If we restrict our one-parameter family such that we have an 8a to the mu that is lie dragged by k to the mu, we then have see the next equation shown. So equation 6-44. This would then give delta k to the alpha equals the fraction with numerator d8a to the alpha and denominator d tau, so that we would have equation 6-45. Considering the alpha equals 0 times cas colon the fraction with numerator d of delta k to the 0 and denominator d of tau equals 0 to lowest order. So, in tensional form we have to lowest order, equation 6-46.
The geodesic deviation equation with the restriction on our one-parameter family such that 8a to the mu is lie dragged. Generalizing the one-parameter family using the tensional nature to an arbitrary coordinate system, we have the geodesic deviation equation, undoubtedly in a manner very much like Levi-Civita's original deviation as we are working in Fermi coordinates as he did in his paper. If we do not restrict ourselves to one-parameter families that follow from a lie drag displacement vector, we have the desired general equations. Equation 6-47. Equation 6-48. 6.4 Derivation of deviation.
Consider a 2D submanifold spanned by gamma sub s of t, denoted sigma. Gamma sub s, a one-parameter family of geodesics, tangent t to the a, deviation x to the a map t, s goes to gamma sub s of t is smooth, 1 minus 1, with smooth inverse. Gauge freedom, in x to the a underchange of affine parameterization, by rescaling t by an s-dependent factor x to the a can always be chosen orthogonal to t to the a. Thus, the Lie-dragging relation can always be solved, coordinate vector fields, and we get the geodesic deviation equation.
So, we have geodesic equation as the simplest parameterization to study. Equation 6-49. K sub 0 to the mu 8 a sub mu equals 0 with perm. That yields geodesic deviation equation. Equation 6-50. Equation 6-51. Where curly and sub j to the I equals the ik of g curly and sub kj etc. The gauge freedom used to specify a coordinatization of sigma results in a specific vector field for the tangent vectors, which is one case among many, certainly of measure 0. A different gauge of rescaling will yield some other vector field.
General equations, equation 6-52. Equation 6-53. Now see the equation. So, 8a to the m is a function of tau colon the m of 8a equals the m power of 8a of tau and can be found by the geodesic deviation equation. See the next equation shown. Thus, see the equation. And delta k to the I equals d8a to the I over d tau plus co and stant equation. 6-54. So we have open bracket 8a, k close bracket equals a to lowest order.
So, to lowest order in the deviation equation, equation 6-55. Solve for 8a to the I, equation 6-56. Difficulties using a one-parameter family of the geodesics when we're partly interested in that instance when the analysis fails, i.e. the formation of caustics. Suppose we start with geodesics deviation, equation 6-57, and the geodesic equation, equation 6-58, and using Fermi coordinates, equation 6-59.
Where a sub alpha beta gamma delta are the components of the Riemann tensor along the world line x to the j equals 0. Assuming I've evaluated our sub alpha beta gamma delta vertical bar sub g. First the symmetry relations and definitions, see the group of equations. Now the g's. G sub 0 0 equals negative 1 minus R sub 0 script L 0 m times x to the script L x to the m. G sub 0 I equals negative 2/3 R sub 0 script L j m times x to the script L x to the m.
G sub ij equals delta sub ij minus 1/3 R sub I script L j m times x to the script L x to the m. Now the gammas. See the equations shown.
And see the following group of equations. Since the gamma primes are O of the absolute value of x to the j and the alpha sigma of g sub comma mu is O of the absolute value of x to the j, while the alpha sigma power of g of gamma sub sigma beta delta gamma is O, constant. So we need only consider.
See the group of equations.
And see the equations shown. Have our sub alpha of open bracket beta gamma delta close bracket equals 0 times and times our sub open bracket alpha of beta gamma delta close bracket equals 0, so.
See the following group of equations. Perhaps a FNC system can be generalized to any geodesic or non-geodesic, it already has been to some extent, by merely writing equation 6-60, and then derive a, b, c, by calc our sub alpha beta gamma delta along chosen geodesic and equating. See Levi-Civita, Meth. and 97, 291, 1926, or J. L. Singh. Relativity, the general theory to verify. Riemann coordinates gives. Satisfy gamma sub mu v to the sigma equals 0 times a t times a times SING of LE times POINT. Equation 6-61.
CL. P. Eisenhart-Riemannian geometry. Levi-Civita, in the paper above, developed for the first time the equation of geodesic deviation and used Fermi coordinate as a technique for simplifying this equation to display its properties more clearly. We will now retrace a summary of that effort. Consider to start, see the group of equations.
In FNC, see the equations shown. So, see the next equation shown. Since the fraction with numerator d of k to the 0 and denominator d of tau equals 0, we get see the equation.
Thus, see the following group of equations. So, we must consider the other factors. 0 order have equations 6-62. First order have 2 infinitesimals delta k to the alpha and delta k to the mu, equation 6-63.
Second order equation 6-64. Consider a one-parameter family of geodesics CS, where S is not affine param, but an index, with tangent vectors k to the alpha, S, and associated conventions gamma of C of S. Equation 6-65. For geodesic equation, we have C the group of equations. We have C the next equation shown,
where k to the alpha has only alpha equals 0 component, and see the equation. Only have gamma sub 0 ij and gamma sub ij k non-zero, which implies gamma sub beta mu to the alpha k to the beta equals 0 and gamma sub beta mu to the alpha k to the mu equals 0. Thus, equation 6-66. Thus see the next equation shown. For alpha equals 0 see the equations shown.
And see the following group of equations. And for alpha equals k see the equation. Recap, see the next equation shown. Is the tangent to curve tau of x. See the equation.
For gamma sub 0 beta to the alpha equals 0 over bar only have gamma sub 0 ij and gamma sub ij k non-zero on fundamental geodesic. See the group of equations. Thus see the equations shown. Since gamma sub 0 mu to the alpha equals 0. So, to first order in delta k to the alpha.
Equation 6-67. 8a to the mu vertical bar equals 8a to the mu projected orthogonal to k to the alpha geodesic should exhibit the same growth with affine parameter as that for the displacement of a geodesic with delta k to the alpha equals c(t) period along that affine parameter, thus linear growth. Geodesic equation gives lowest order behavior. Linear. Geodesic deviation equation gives up to second order ODE behavior. So can see oscillatory or exponential. What is C the next equation shown? Our sub 0 0 gamma to the mu vertical bar sub g has our subscript L0 m to the 0 term as expected.
To lowest order have C the equation. Our sub I script LJM equals our sub I script LJM vertical bar sub g rest have displacement factor, higher order. So, see the next equation shown. And, thus see the equation. To lowest order equation 6-68. Equation 6-69. Can have exponential and oscillatory, 8a to the mu terms. Use of FNC implies no rotation of geodesic, so curly and sub v to the mu has only expansion, contraction, and shear.